In today's video, we'll see how work is performed on a gas. When work is done on a gas at a constant pressure, we can define work with the following equation that states that work is equal to negative pressure multiplied by our change in volume, where P is the pressure throughout the gas, and our change in volume is a change in volume of the gas during the process. So if we have a gas that is compressed, we see that our final volume will be less than our initial volume, making our change in volume a negative value, and the work done on the gas therefore will be positive. If the gas expands, then we see that the final volume will be larger than our initial volume, making our change in volume positive, and the work done on the gas negative. And we sometimes say that when this happens, the work is done by the gas instead of done on a gas. If we look at work done by the gas, we see that work from our environment is the negative of the work done on the gas and can be seen below. The negative work is equal to our work done by the environment. So we saw how we can calculate work by taking our negative pressure, multiplying it by our change in volume. However, if we're given a pressure versus volume graph, we can use our PV diagram if it's an isobaric process where the pressure remains constant while the volume of the gas is what changes. We can use the area underneath the graph to calculate the magnitude of the work done on the gas. And we see that this is summarized in the equation below. So if the arrow from the initial and final state points towards a larger volume, then the work done on the gas will be negative, and if the arrow points towards a smaller volume, then the work done on the gas will be positive. So when negative work is done on a system, positive work is done by the system on its environment, since no energy is lost within the process. And if we look to our right, we have a few examples of what a PV diagram would look like. So if we looked at each individual graph, we can see that without even looking at the area underneath the graph, we can see that our first graph will have negative work done on the gas, we'll have a positive work done on the gas, and in graph C we see we'll have a negative work done on the gas since its volume is expanding, and a positive work done on the gas in graph D since our arrows point towards a smaller volume. In our example given, it states that 1 mole of an ideal gas initially at a temperature of 0 degrees Celsius undergoes an expansion at a constant pressure of 1 atm to 4 times its original volume, and we're asked to calculate the new temperature of the gas. So we summarize the information we're given that we're given 1 mole of a gas at a pressure equal to 1 atm, and our final volume is 4 times our initial volume at a given temperature of 0 degrees Celsius, and we're asked to find the final temperature. Well, by using the ideal gas law, which states that PV equals nRT, we can rearrange our equation where nR is equal to PV over T. So we can say that our initial volume and our initial temperature is also equal to our pressure times our final volume divided by our final temperature. Since we're trying to solve for our final temperature, we can rearrange the equation where we'll get our final temperature is equal to our pressure times our final volume multiplied by our initial temperature divided by our initial pressure multiplied by our initial volume. And so since our pressures remain the same, we're left with the equation that our final temperature is equal to our final volume multiplied by our initial temperature divided by our initial volume. So we can write the equation that our initial temperature multiplied by our final volume, which was 4 times our initial volume, divided by our initial volume. We see that our volumes will cancel out and that our initial temperature was 0 degrees Celsius. And after converting it into Kelvin, our initial temperature would be 273 degrees multiplied by 4 will give us a final temperature that is equal to 1092 degrees Kelvin. And in part B, we're asked to calculate the work done on the gas during the expansion. So we know that work is equal to our negative pressure times our change in volume. And if we multiply our pressure through, we'll get an equation that states that our pressure minus the pressure of our initial volume. And since we know that PV is equal to nRT, we'll have an equation where we'll have nRT final minus nRT initial. We can substitute our nR out of our equation, and we'll be left with our final temperature minus our initial temperature will equal our work. Since we know how many moles of gas we have, and R is a constant, and we calculated our final temperature in part A, and our initial temperature is given to us, we can calculate the amount of work that was performed on the gas. So we're given that we have 1 mole of gas multiplied by our universal gas constant of 8.31 times our final temperature of 1092 degrees Kelvin minus 273 degrees Kelvin will give us a value of work performed to be equal to negative 6.81 kilojoules of work performed on the gas. And this negative value sign should make sense since our gas is expanding, so our final volume is larger than our initial volume, meaning our change in volume is positive, meaning that our work will be negative.